Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, continuing our idea of last time talking about optimization and maximizing area or area equivalence. So let's jump in with a little bit of a review of what optimization is. In general, we want to maximize or minimize a quantity. So in our geometric applications here, we're typically looking to maximize area. We're also going to quick look at maybe what happens if we try to maximize volume. And we're subject to some constraints. So in this case, we're typically looking at a fixed perimeter around the shape, or then in 3D, we're going to examine quick today the volume and surface area, and those would be the constraints there as well. So, review of an inequality, right? So when you're solving these things, there's a lot of methods, but they get complicated pretty quickly. I'll talk a little bit more how these things typically are pretty difficult later today. But I want to remind us of this AIME inequality that we looked at last time. So it says for n numbers, the arithmetic mean, so the sum of the numbers divided by how many there are, is greater than or equal to the geometric mean, which is the nth root of the product of the numbers there as well. So let's do a quick example, and this is what we're going to need today for the most part. When n is equal to 3, we can say, and I'm going to just switch the variables around a little bit here, the sum of x, y, and z divided by 3 is greater than or equal to the cubed root of the product of those three numbers. So the product of those three is x, y, z. Take the cubed root of that. That is less than or equal to the sum divided by 3. And so we could rewrite this in different ways. I'll rewrite it in a different way in just a moment as we use it to help answer the example of triangles. So we did the square last time. We have the general inequality for 2D shapes in a little bit. But prove that if you're thinking about triangles, the maximum area of all triangles with a fixed perimeter is when you have an equilateral triangle in this case. So the hint is that by Heron's formula, the area of a triangle with sides A, B, C is square root of s times s minus a times s minus b times s minus c in this case, where s is half of the perimeter. So that's what we're going to have in this case. So let me just rewrite it here for a moment, and we'll use this on the next screen. But really what we're saying here is the area squared is s times s minus a times s minus b times s minus c. And then, let's just not write it down, but remember that the s is half of the perimeter in this case. Okay, so how can we look at this for our triangle maximum area? So let me put our a squared up at the top here. And off to the side, let's do the AMGM on the right-hand side here. And we're not going to need all of the terms or things like that. But let's remember our XYZ one. So let me write it out here, the cubed root of the product XYZ. This is now, I'm switching the order a little bit, but this is less than or equal to x plus y plus z divided by 3 in this case. So we have that divided by 3 there. So what are we going to look at in this case? Well, of course, we have the product of these three things, s minus a, s minus b, s minus c. Notice the s itself is like a perimeter divided by 2. So that is in terms of the perimeter. Let's see if we can manipulate this portion into something like that too. So Another rewriting of this is that the product of these three, so let's cube both sides, is less than or equal to x plus y plus z cubed divided by 27. And this is actually the one that we want to plug in this scenario. Now, why is that? Well, let's look here at what happens when x is s minus a. This is just going to save me a little bit of writing here. At y is s minus b, and z is s minus c. So the product is the product in this case. But something nice happens when we look at x plus y plus z. Well, x plus y plus z, wait a second, that's 3s, right? So we have 3s here, and then we have minus a plus b plus c. So we're subtracting those three things in this case there. But wait a second, a plus b plus c is the perimeter, so that is 2s. So this is 3s minus 2s, and so this is equal to s in this case. So the nice thing that happens here is actually this product xyz is less than or equal to s cubed over 27. So actually all of that stuff with the a, b, c, right? All of those things work out nicely and cancel out. And so this actually gives us an inequality here just in terms of the semi-perimeter in this case. So let's plug all of this back in. So this is a less than or equal to. So now we have a squared is less than or equal to s times s cubed over 27. Basically here, this is equal to s to the 4th power divided by 27. Now we're dealing with positive areas, positive perimeters, all of that fun stuff. So let's just not worry too much here about taking the square root. And we can say that the area is less than or equal to s to the 4th square root is just s squared. 27 square root is 3 root 3. So we have 3 square root of 3 in this case there. Now, this is in terms of the semi-perimeter S. So one final thing here for our equilateral triangle, right? We want to show that the area is equal to this in an equilateral triangle case. So if we have an equilateral triangle, so let me abbreviate this as such. So let's say we have an equilateral triangle with side length x. So the side equals x in this case. So that means all of the sides are equal to s. Now what does that mean about the semi-perimeter? Well, the semi-perimeter is x plus x plus x divided by 2. So the semi-perimeter is 3x divided by 2 in this case. So if we plug that into our equation, right? So if we plug that in, 3x over 2 squared divided by 3 root 3, right? The area in that case is equal to this, right? So we basically have a 9 divided by 3 root 3. That's a 3 root 3. X squared in the top, so that cancels out everything with the 3's except for a square root 3. And then we have a, x squared, and then we're dividing by 4 on the bottom. So this is actually the area we get in that case, right? And so that is exactly what we want, right? So the area is equal to that. That is s squared over 3 square root of 3. Right, so let me say that this is equal to this here. So we do have equality for an equilateral triangle, which is what we wanted to prove in this case. And as mentioned last time, a lot of the symmetry stuff helps here as well. So this result shouldn't surprise us too much, but it does need a pretty fancy inequality or a higher level inequality in AMGM to at least give a nice proof in this scenario. Okay, so let's look at our second question then. And that's trying to fill in this blank. Can we give a general inequality for, okay, how does the perimeter relate to the area? We saw one for the triangle, we did it for the square, but what about for general shapes? Now, if I'm saying more symmetry, right, helps, things like that, the hint we gave last time shouldn't be too surprising, right? So a circle actually has the maximum area for a given perimeter. So, right, why is this not surprising? Well, for 3 sides, it's a triangle. For 4 sides, it's a square. For 5 sides, 6 sides, right, we get more and more close to a circle. So in general, the circle has the maximum area for a given perimeter in that case. So how can we check what number should go in here? Well, remember this is going to be equality then for a circle. So let's start looking at things in terms of the circle. So A for a circle is pi times the radius squared, right? P for a circle is 2 pi r in this case. Now, of course, we don't actually want to be dealing with r, right? We want our inequality here to be involving just p, right? So let me put off to the side our blank. We want to say p squared is greater than or equal to something times a in this case. But we can just substitute r in this scenario, right? So the second equation says here, so r is equal to p over 2 pi. And then plugging this in for a, so then we have a. So a is pi times r squared. So let me just square this right away, actually. So we have p squared over 4 pi squared. And canceling the pi's, we have p squared over 4 pi. So this is supposed to give our maximum scenario, right? In this scenario, p squared is equal to 4 pi times the area in this case. So the area is less than or equal to p squared over 4 pi. And so that tells us that in general, that's what goes here as well. Because circle is our max, so that gives us the constant so that when we plug in a circle, we would get equality in this scenario. So p squared always greater than or equal to 4 pi times a in this 2D version of things here. Now, it shouldn't surprise us too much that we could have a 3D version of this as well, right? So what happens if we have a 3D versions of this in this scenario? Now, I'm not going to do the full proof here in this case, but again, this shouldn't surprise you that stuff is involving around a sphere, right? So we can do something very, very similar in that case. So what do we get there, right? Well, our goal is to find, right, given a surface area, we want to find the maximum volume V, right? And so in general, we have this inequality in 3D. It says now things are getting a little bit higher powered. So we have the surface area cubed, right? So surface area cubed is greater than or equal to 36 pi times the volume squared. So here we have a volume squared in this scenario. So that's what we have then in this case. And you could do this in general, but we're not going to focus all that much on that today. But I do want to stress a little bit here at the end that this optimization is not easy. This is a difficult thing in general, right? When you're formulating this, you have to ask, what are we maximizing or minimizing, right? What are the constraints? Notice those constraints might be more difficult than you think. In fact, just with these inequalities we're doing today, what does it mean to be a 3D solid, right? Are there restrictions you want on the curves? That is actually pretty hard to decipher mathematically. and describe mathematically there, right? The different constraints, maybe if you're doing applications, you have to think about those, right? And be careful with what constraints you're given. And, right, it can be difficult using pure mathematics. So the simplest and nicest proofs of even the 2D inequalities we're doing today typically involve calculus, arc length formulas, integrals, things like that there. And so a lot of the times computer science algorithms can help give both optimal solutions. So there's times when you have a certain type of optimization problem, like a linear optimization, there's nice efficient algorithms to give you optimal solutions. Or sometimes even if there's not optimal solutions, you can get approximations. And I do want to stress, typically when we're talking about a mathematical approximation or a computer science approximation, you know something about that approximation. You typically have a good idea how well that approximation will perform. What is the probability that you have a good approximation? So it's not just like, oh, the algorithm gives you, here's my best guess, and you say, well, what do you know about that guess? Nothing, this is just my best guess. No, they can say stuff like, I'm not being honest with the algorithm saying something, but you know that the algorithm is giving you something that, okay, 99% of the time, this approximation will be within 5% of the correct answer. Things like that can be shown and proven, and that's a big portion of how optimization is typically done today. So that will bring us to the end of this video. If you liked the video, please hit the like button below, subscribe for updates each week. Next week, of course, we'll be starting a new topic. So if you have ideas for topics you would like to see in the future, let us know in the comments below as well. Thanks for watching. Goodbye.